All right, so welcome to this guest talk from Yoshua Bengio. As you know, Yoshua Bengio is a big deal in machine learning, and at Mila, a lot of people are working on this area called causal representation learning, so I figured Yoshua would be a great person to give a talk on this. So with that, I'll go ahead and give it away to you.
Thanks, Brady. Yeah, indeed, what I'll talk about today is at the very heart of my research program. So a lot of it is more aspirational than results, but I'll mention a few papers that we've been working on in the last couple of years in this area. In a way, it's also about how deep learning, which is really representation learning, can bring something important and different to the decades of work in causality that are behind us. And here it says an AI and deep learning perspective, because I think that representation aspect is part of a bigger picture of the questions you would ask if you think about how a baby comes to understand the world, or how a robot might act in the world in order to understand the world. So these are the kinds of questions that the AI researchers are thinking about, which are different from the traditional questions that causality researchers have been thinking about, which were tailored at, say, social scientists trying to know if, or medical scientists are, trying to know, is smoking causing cancer and things like that. So this is a very different kind of thinking about causality that's more centered on how would a learning machine act and organize its understanding of the world to make better sense of it, be able to control it, be able to achieve its goals. All right, and now, why would machine learning people even care about causality, which seems to come from kind of outside of machine learning field? And I would say that there are pretty significant gaps between current state-of-the-art in AI machine learning, machine learning-driven AI, and the intelligence that we see deployed in humans and many animals. In particular, one way to summarize this is the very difficult to formalize word of understanding. We don't have AI systems which actually understand at the level that humans do, or anywhere close. So what does understanding mean? It's clearly something that nobody has a complete answer to, but I think it's driving a lot of this kind of work. And in part, it means capturing the causal structure in the world. Maybe not the perfect causal structure, because humans don't have a perfect model of the world, but enough to figure out what would happen if, enough to plan, and be able to do it at an abstract level. This is a really important aspect that's connected to the notion of representation learning, because I think there's causality, as you might think about it, say, if you're a physicist and you think about causality as a principle for organizing information flow at a physical level, like atoms and the forces of nature and so on. But the kind of causality that humans really exploit is very different. We don't model the world at the level of atoms and microseconds. We model the world in terms of these aggregate variables that are, involve a lot of lower level things in a single concept. And these are abstract representations and abstract actions. And they are inventions. They don't exist. In a sense, they don't exist. They're constructions of the human mind. Sometimes we can estimate them, we can measure them. But what I mean by they don't exist is, we could construct many other representations of the world. It's just our mind has come up with these abstractions, and these abstractions are incredibly useful. That's the reason evolution and culture and individual experience have, built this into our minds. They allow us to control aspects of the world. They allow us to reason, plan, and as I'll go a lot in depth into, they allow us to face non-stationarities, to face changes in the world, novel scenarios, and come up with meaningful interpretations, meaningful actions that work pretty well. They also allow us not just to act, but to learn. Because if you think about a lot of your learning, it's tied to inferences you're making that allow to do credit assignment. Why is it I'm, I don't know, failing my exam today? Is it bad luck, or is it that I didn't study very much over the last week? Right. So these are inference problems. They matter for credit assignment. In other words, for learning. So it's important for actions. It's important for learning. It's important to deal with generalization out of distribution. These are very powerful and strong motivations for machine learners to think about causality and bringing it into their work. So I'm going to go through a number of aspects of this in a bit more detail in this lecture. Number one is learning theory. Learning theory, I was a witness to the early days, at least of the learning theory and machine learning in the 80s and 90s with Vladimir Vapnik, for example, who was my office mate at Bell Labs in the early 90s. And it's all centered on this IID assumption, or more generally, simply the assumption that the test data are sampled from the same distribution or the same process as the training distribution or the training process. It's a very powerful assumption. It looks like a little assumption like this. No, it is central. If you didn't have this assumption, all of learning theory falls down. And you can imagine that if you don't assume anything about what you're going to see next, how could you have any kind of guarantee that you will generalize? The reason we have those bounds in learning theory is because we're making that assumption. It's a very powerful ingredient. Unfortunately, it's not a realistic assumption. I mean, it was fine if you were looking at handwritten digits classification, and even then, comes people from a different culture, and they write their sevens differently, as we know, between Europeans and Americans, for example. And then your bounds don't work. This is something, if you're working in industry, you see every day. We train machine learning models. They then, on data that was collected in a particular way, and then you test them or you deploy them, and it doesn't work as well. So somehow machine learning needs to come up with a way to deal with those changes in distributions and non-stationarities. And incorporate that in its theory. And so we need alternative assumptions. There's no way around it. If you make no assumption, you're dead in the water. I mean, maybe it's going to work, maybe not, but you can't really know. And I think understanding the assumptions also will have an impact on the kinds of algorithms that are needed to take advantage of the particular structure of these assumptions. So when you think about how humans manage to generalize in new settings, one of the ingredients that is also connected to the question of causality. So causality will help us form a theory of how things change in the world. And the other thing that is in a more subtle way, and be part of my message, that thinking about causality will help us is knowledge representation. So the way that a human being is able to face a new situation, like say you're driving in a new country where the traffic laws are different. Somebody tells you the new, the change in the traffic laws, and it's going to take you a lot of attention, a lot of thinking and presence to what you're doing. But very likely you'll be able to reuse the knowledge you have, the knowledge about driving, the knowledge about traffic laws, knowledge, general knowledge about language, to come up with a policy that kind of works in this new environment. It could be fine-tuned later as you collect more data, but you're going to get zero-shot generalization. Humans are very good at that. And then as you get a little bit of data, very little, you can adapt it and quickly gets better. And then, of course, it will turn into a habit as you practice more, and you won't need to think about it. So part of that is, how did your brain break up your knowledge into these pieces that can be recombined and reused as needed on the fly, even in ways that were never seen in your training set? Okay. So that touches on the question of compositionality. Compositionality is probably one of the core concepts in computer science, if not in mathematics. And one of the reasons why I didn't leave the research track on neural nets in the late 90s, when everybody in machine learning was kind of going away from neural nets, is because I realized that there was something about neural nets in terms of compositionality that was missing in the other methods that were popular then for machine learning, in particular kernel methods, which were dominant in the late 90s. And so, I mean, in an intuitive way, this is being presented already a long time ago in the early 80s, especially by Jeff Hinton, who's being a big proponent of the notion of distributed representations. And then in the 2000s, the work we did with many colleagues on deep nets, especially with more layers, also involves a form of compositionality. Right? So in the case of distributed representations, is different features can be combined in an exponential number of ways. In terms of deep nets, is the composition of functions one on top of the other that gives you power. And in both cases, you can show mathematically, and it came a few years later because math is slow, that indeed you can potentially have an exponential advantage from these forms of compositionality. But there's another form that we need to address, another form of compositionality. It's a form that we find in language, for example, that the linguists are familiar with. I think it's a form that allows humans to do analogies and abstract reasoning. And that's a form which could be called systematic generalization. And you have a visual example here. Let's say these vehicles, but now you see the red thing, red vehicle at the bottom. Your brain can make sense of it given the other vehicles you've seen before by combining somehow aspects of these other vehicles. And even if the probability of seeing such an example in your training distribution was 0, your brain can manage to make sense of it. We can see this, like if I tell you a science fiction scenario or my example of driving in an unknown place. And furthermore, our current state-of-the-art systems, essentially deep learning systems, they don't seem to be that good at it. Now, this raises an interesting point. It's very important. There's a difference between overfitting the training data and overfitting the training distribution. So normally in machine learning, we think about overfitting the training data, and that means that we don't do well on the test data from the same distribution. But now we're starting to talk about changes in distribution. And so you can overfit the training distribution, meaning if you have a test set from the same distribution, you're going to do well. But if you have a test set from a different distribution, you might not be very robust. And so a few papers have investigated that failure. But as I said, it's actually a common industrial problem. Now, a big part of my presentation today is also to look at humans, because they seem to be key to making sense of solving this problem. Because humans do a very good job at generalizing out of distribution. And as I said with my driving examples, it seems that the way your brain operates is different when you're, say, driving in your usual route and you don't have to think about it, versus when you're driving in this new city with new traffic laws. You can record what's going on in your brain. Well, not while you're driving, but other experiments, and you can see that different parts of your brain are being activated, and that they actually are very different patterns of activation and processing that neuroscience is now helping us understand. There's still a lot of questions about this conscious processing in neuroscience, but we know a whole lot more than 30 years ago, before fMRI and all that started. So why making all this point is that we have a living demonstration of how to deal with these changes in distribution that are, as I'll explain, I think are connected to causality. And I think we can get inspiration from what neuroscientists are doing to figure it out in brains. And in fact, we can do even better than that. We can use machine learning as a theoretical tool to provide scientific hypotheses about how brains might be doing these things, because neuroscientists are observing, but they can't do the sort of simulations that we can do in machine learning that may help to see, well, the devil is in the detail. Like, how would you do this in a neural net that's artificial? Maybe that gives us ideas about how the brain might do it. Okay. So out of distribution generalization, I already mentioned it. And what I want to say is there is also a deep connection between the need to generalize out of distribution and the fact that human beings and the robots we'd like to build in the future are agents. So agents means action. That's the same root. Means that you interact with your environment. And when you're not in a static, if you're not a static passive observer, if you're allowed to do something, that action may change distribution. If I lock a door and I throw away the key, this corridor is not available anymore. The world is a different place. You can't plan in the same way. So the non-stationarities naturally come up for agents. What gets even worse is if you have multiple agents. So you interact with somebody, and there's no stationary distribution, and we never get to the point where everything is stationary. It would take infinite time. In practice, the world keeps changing in ways that are always different from what happened before. And that because of the interaction of agents. Yeah, there's a question. Oops, sorry, that's my fault. Just a second. I'm going to fix that.
It looks like a question did pop up in this pause. It says, Brady talked about the causality, illusion, cognitive bias of humans confusing correlation with causation. Do you think AI should overcome that superhuman or perhaps exploit that fuzzy causality? Thank you.
I don't feel like we are in a good position to talk about superhuman things because we are so far from human level performance. And that being said, I do think that humans are able to, if they have the right knowledge and the time to think, to separate causation from correlation. Now, we also make a lot of mistakes, and often it's it's because it's a hard job and we're missing pieces of the puzzle, or we're not thinking enough. But eventually, some humans figure it out, and this is how science progresses. So it's fundamentally hard to make sense of how the world works, and I don't think we should blame humans too much. What we should do is consider their biases, and not as something bad, but something that's a clue to try to address about how brains address this. They don't solve it. Nobody can solve it. solve these problems. So as we build machine learning systems that try to solve the same problems, maybe some of them, some of these approaches might be closer to how humans do it, and that would be very instructive for many reasons. All right. Should I continue? If there's no other questions, I'll go on. There's nothing else, Brady?
Yeah, no other questions.
All right. So let me now introduce a notion. You probably heard me already talk about this, but that's connected to this conscious processing thing I was talking about. Psychologists have been trying to divide different cognitive abilities in different categories, and there are two broad categories that emerge that are well described in Dan Kahneman's Thinking Fast and Slow. Very nice book, easy to read. And by the way, and Dan Kahneman is a Nobel Prize winner in economy, but really it's a lot of psychology that he's talking about. So system 1 and system 2, as he calls them, and I may not exactly follow the same lines that he has in his book, but I'm going to lump this with some of my understanding coming from a machine learning perspective, and break down the types of cognitive computations that are going on in our brain into these two categories. System 1 is where current deep learning is really very good, intuitive, fast, unconscious, meaning we can't really explain how we got there. Very much parallel, just a few steps in your brain. Like if everything you can do in half a second, right? That's in that category. Not really linguistic, and again, the sense that you can't easily put words on how you did it, and it corresponds to your habitual behavior, where you don't need to think about it; it just happens. System 2 is everything else, right? So everything you can do that you can explain. Everything you can do in your mind that you can explain, right, to someone else. So it's usually logical, sequential, conscious. That's what allows you to report about it. Linguistic, we can use words to describe it, and that is how we do a lot of computer science. Algorithms, right? Algorithms are just a sequence of instructions. A lot of our planning depends on that, although planning also depends on system 1, and a lot of reasoning similarly. So what I'd like is us to extend deep learning to those system 2 tasks. So that includes dealing with causality, but much more. And another interesting division that has to do with the conscious access is implicit versus explicit knowledge. Right? So as I said, the system 2 part of your knowledge of the world is something you can communicate with other humans, but in fact, it's very likely the vast majority of the things you know about the world are implicit in system 1. You can't really teach someone unless you help them practice, for example, which is a different story, not explicit. So it looks like there are aspects of how the world works which are verbalizable and aspects which are not. And we might wonder, how did this state of affair come up in terms of evolutionary process, both culturally and genetically? And a plausible hypothesis is that the verbalizable knowledge satisfies some stronger hypotheses than the non-verbalizable knowledge, and I'll go through that in detail. The things we can verbalize have a special property, and basically you can summarize it, you can verbalize it. Whereas there are lots of stuff that's just too complicated, we can't verbalize them. So what does it mean too complicated? We're going to try to unpack that. But that's if it was true that some aspects of the world had had these constraints, then we could build machine learning systems that take advantage of the corresponding inductive biases to learn about the verbalizable part And they would probably need to be different inductive biases than the ones we use for system one and the things we already do with deep nets. So then I think a good scientific question is, what are these inductive biases? What are these assumptions that go in the verbalizable camp? And now I'm going to talk about an underlying assumption that actually comes from the work on causality, which is behind a lot of these things, but not all. It's a concept that I learned from Bernard Schopkopf that he talks about in the paper in 2012, the notion of independent causal mechanisms. And the idea is we can explain the world by the composition of informationally independent pieces, independent mechanisms. Okay, what does this word independent mean here? It doesn't mean that the random variables corresponding to the inputs and outputs of these mechanisms, the typical random variables in the graphical model, it doesn't mean that these random variables are independent. This is informationally independent in the sense that the description of those mechanisms, like in the Kolmogorov sense, the description of these mechanisms, if you want, the parameters, if you think in the Bayesian sense, the distribution over those, if you think of the parameters as random variables, like in Bayesian sense, and these are independent. In other words, when I learn about one of the mechanisms, it doesn't tell me anything about the others. And if it did, it means I didn't decompose my knowledge in the right ways. Now, this is a story I'm talking about, right? It's an assumption that we can explain a lot of the world by factorizing it in these independent pieces. And I believe that humans are exploiting some form of that. Now, why? I mean, it's a very powerful assumption. And one consequence of this that we've been exploiting is what happens if you change one of the mechanisms. And this is where causality comes in. An intervention, a causal intervention, will typically be affecting just one node of this graph, one mechanism. Maybe we fiddle with the mechanism itself, or we fiddle with the output of that mechanism. And so why this particular decomposition would be useful? Because agents will typically be only able to act in one place in the world, in this kind of model of the world that we imagine in people's heads. The abstract actions and the concrete actions that agents can do typically will only touch one of these things. And of course, there will be consequences. If I push the cup, it will fall, and many bad things can happen. But it starts with a single abstract action here, which is pushing the cup off the table. If we were to organize our knowledge in a different way that wouldn't have these properties, then it's not clear that the intervention of an agent would be summarized by a single point of intervention or very few points of intervention. It might think about just do a rotation of the representation space, and now I do one thing and everything gets to be affected, and it becomes much harder to figure out what happened. And a lot of what your brain is doing is figuring out what happened. Something happened out there, and your brain is always seeking to figure out what's the cause of what we're seeing, and especially if it's unusual. So this is a key advantage. And if only one bit changed somewhere in kind of my representation of the world, then I can do inference to figure out what that bit was, or I can adapt my model with very little data. And that's, of course, of great value from a machine learning perspective. One additional thing here, which is sort of corollary of the assumption of informationally independent pieces is that if the same piece, like, the law of gravity, is applied on many instances, like many objects, you should not consider these different instances as having their own version of the mechanism. You should really think of it like it's a shared mechanism. There's only one, say, gravity constant or something. So if we build models like graphical models, they need to have this property that you have a parameter sharing structure that allows the same module, the same mechanism, to be applied on many instances of variables where it makes sense to apply them. So, as I promised, we're going to make assumptions, or rather, we're going to try to think about the sort of assumptions that humans may exploit to model that system 2 aspects of the world. So here's a list, and in the rest of my lecture, if I have time, hopefully it should be fine, I will go through many of these. But let me give you a preview, and then we'll go in more detail for each. This is the way I've been taught that teaching works. So the first one, it says sparse factor graph in the space of high-level semantic variables. So really, this is only saying that the sort of dependencies that exist between those causal semantic variables that we think that the human brain is manipulating consciously, that those dependencies are sparse. Right? Each rule that tells us about the dependencies between some variables involves very few arguments, very few variables. Right? So that's number one, and we'll see why it makes sense and then how that could be useful. Another one is that those variables have something to do with causality, and you can see that in language. Right? Words refer to agents like people, animals, and so on. They refer to intentions and actions that have to do with how cause creates effect. And they talk about objects that can be effects, controllable objects. Right? And of course, objects can cause other objects to change in the chain. Another assumption that I've already mentioned is that the changes in distribution. Remember, we started this lecture with the challenge of dealing with changes in distribution. Those changes in distribution are due to causal interventions for the most part. That means that they are local in the right space of representation, in this semantic space. If you have the right space of representation, then the change should be explainable by a few words. And there's a kind of proof of this, hand-wavy proof. Think about how humans explain things that have happened. And they usually are going to use language to describe. So language, a sentence, that's very few words. And if it takes much more than a sentence, maybe, a whole paper or something, then we'll invent a new word. We'll invent a new term to talk about a new abstraction that we need to add to our model of the world in order to, again, make the explanation compact and involve just one or very few variables. Fourth assumption, which I'll mention quickly, is that is that there's a simple mapping between those high-level causal semantic variables and language, words and sentences. And that's an immediate consequence of the connection to conscious processing. Everything that's happening at a conscious level, you can report with language. That motivates this assumption. I already mentioned, and as a consequence of the informationally independent causal mechanisms sort of theory, that you're going to need to share the same rules, the same mechanisms across instances. And when you do that, it begs the question of variables, right? So if you want to talk about a rule that can be applied to many possible instances, when you define that rule, it's like a function in programming. Like you want to define it in terms of placeholders that are like variables, and so you need some form of indirection in the way that you're processing information. And these notions of variables and indirection are not very present in the standard classical feed-forward neural nets, but they become crucial here. Another assumption.
I have a
Yes.
question we just established that most of our knowledge is not verbalized. How will we be able to divide that knowledge into pieces?
You mean the verbalized versus non-verbalized, right? Or the different piece. Oh, the different pieces in the non-verbalized part. Is that the question?
Yeah, I think that's my
interpretation. Yes. I don't know. And maybe we don't need to worry about it. So for now, I'm just going to worry about dividing in pieces the high-level knowledge, because we don't even know that it's possible to modularize it in the way that I'm thinking about at the system one level. So I think things might become clearer down the road of this lecture, but I would say one important message I'm trying to carry is system two computations, which involve this high-level knowledge, cannot stand on its own. There are exceptions. Like if you do pure logic, you can do it all like this. But a lot of what's going on in the world, it's not enough to involve only the sort of system two conscious processing. In fact, almost every time you reason, you call upon system one computations to help you research or to help you implicitly connect those high-level concepts to the kind of low-level perception and low-level actions that you need to really give meaning to these concepts. So what I'm trying to say is maybe we don't need to worry too much about it, because the modularization will come as a side effect of the system two modularization. And if system one is, if you think of system one as a helper for system two, then it might be okay. And then maybe there are aspects of system one that can't be broken down easily in pieces like this. That's possible. In fact, that's part of our assumption of what makes a difference between system one knowledge and system two knowledge. All right. Sorry if
there's another question.
Yep.
Isn't the non-verbalized knowledge what we have been taught? Isn't the non-verbalized knowledge what we have been taught, as in instructed? If so, shouldn't a counterpart in deep learning be learned essentially data-free?
I'm confused. I don't understand the question. I mean, what we've been taught is verbalizable knowledge, not non-verbalizable knowledge. I mean, we also learn non-verbalizable knowledge, but we learn it through practice. We learn it through imitation. We don't get it through reading a book. So maybe I didn't understand the question.
I mean, I'll let you know if they post more in the chat. But
all right, no problem. Don't hesitate. So my 1, 2, 3, 4, 5, 6 bullet is about timescales. So going back to this notion of changes in distribution, even though and this is again connected to causality, even though the world changes, so I've been talking about that a lot, there are fundamental aspects of it which don't change. So yeah, I pushed a cup down the table, but the laws of physics haven't changed. So there's a lot of the underlying causal structure that remains the same, that is stable. And then there are things that do change, or things that I didn't know that I'm adding to my knowledge. So in a way that it's, I perceive a change. And so being able to separate the long-term stable stuff, which remains true over all these changes in distribution, from the aspects, maybe due to latent variables, right? This is the best way to think about it in graphical models terms. That change from one distribution to another is super important. This is what meta-learning is trying to do in some ways. And an example of that in the brain is in your visual cortex. There are parts like the early layers in your visual cortex that do the low-level vision. They are incredibly stable. It's very hard to relearn them after you're an adult or even a 6-year-old. If we give you some special glasses that put things upside down or something like that, you will adapt, but it's going to take a while, a lot of practice. On the other hand, if I show you a new object that you've never seen, you can kind of make a mental picture of it in your mind and see what's special about it. And with a single example, this is one-shot learning. Okay, so these are two extremes where it looks like there are aspects of the world which we can adapt to very quickly, and aspects that are constrained to be slower to learn because they're supposed to encode longer term knowledge. And the encoder, like the low level vision thing that I was talking about, is a stable aspect, whereas the existence of new concepts, categories, objects, types, and so on, that is something that can change rapidly, and in fact, one shot. The last bit that I don't think I have slides for, the last bullet here, has to do with, again, causality in some way, but the particular aspect of credit assignment. So I mentioned already that conscious processing plays an important role in credit assignment for humans. And if you do a little bit of introspection, you will realize that the sort of causal chains that your brain thinks about to explain what has happened, they're very short. They're surprisingly short, like 2, 3, 4, 5 things. That's at most what we're able to cope with. Otherwise, we need external aid, right? Like a computer or paper and pencil. And so this you may think of as a limitation of our brain, but maybe it's sufficient to solve a lot of the causal learning problems in the world around us, or at least it's an assumption that humans seem to exploit, and eventually machines could push the boundary of that. But understanding these sort of inductive biases may be very useful to build machines that reach human level intelligence. Okay, so hopefully the rest of the lecture is all about going into a bit more detail of this and some actual work to try to explore these ideas. So the first one about sparse factor graphs. Let me do a hand-wavy proof that this assumption makes sense. A lot of sentences in natural language can be viewed as statements about the truth of events. Like, if I drop the ball, it will fall on the ground. And what's remarkable about these statements, so you can think of them as conditional probabilities, right? What's remarkable about these statements is that they involve so few variables. Like this one is just about the act of dropping the ball and the consequence on the position of the ball. Very few arguments. And if you were to try to make these kinds of statements in a different space, not the space of words, but the space of, say, pixels, you wouldn't be able to do that. If you try to predict one pixel given the other pixels in an image, it's not going to work very well if you're only allowed to pick 2 or 3 other pixels. But it works with words. So words or the corresponding, concepts that we manipulate consciously, somehow they have this special property that the dependencies can be captured by a bunch of what I would call, probabilistic rules, which in graphical models term would be factors in a factor graph. So you may have a lot of rules, but each rule is very sparse. Involves, like in the picture in the bottom right, only involves very few variables. So the little squares are the rules or the factors, and the circles are the variables. Now, it's interesting to note that this assumption of sparsity of the factor graph is fundamentally different from the most commonly made assumption in deep learning for learning in an unsupervised way high-level representations. So the typical assumption is that the high-level variables are marginally independent. But obviously, this doesn't work for the kind of causal semantic variables we talk about. The ball and the hand are not statistically independent. In fact, they come together very often. So I think it is important to move away from this marginal independence thing and replace it by this kind of sparse factor graph. Later, I'd like you to note that later I'm going to be talking about attention. Attention is something that humans do and is connected to conscious processing. But it's also something that has been incorporated in deep learning. And in fact, a lot of the interesting ideas came from Mila a few years ago. And there's a connection with attention here. If you were to try to do inference over such a sparse factor graph, there would be many ways of doing it. But a reasonable way, a feasible way, would involve traversing it, going through these variables and these factors. If you traverse the graph, each time you go through one of these factors, you only need to look at a few variables. And so by having this bottleneck of attention that only focuses on a few things at a time, you create a constraint on the type of dependencies that can be captured at the high level. And so one hypothesis for one of the roles of consciousness could be that the limited attention capability of conscious processing is helping to enforce that inductive bias of sparse dependencies at the high level. Okay, second, about the causal connection. I think I've made it already strongly enough. But let me go back to just this clarification. What are the right causal variables we want to be talking about? As I mentioned at the beginning, we can have very different kinds of representations. We could have the causal variables being like the physics variables, like position and momentum of every particle. But brains would not be able to handle that. It would be computationally intractable. Even computers would not be able to handle that, except for maybe modeling a small molecule. And so how do scientists and humans and babies deal with this? They create high-level abstractions. And this is one of the holy grail of deep learning. Learn, discover the right high-level abstractions. And at the top of that food chain are causal variables. But they're not low-level things. They are creations of our mind, as I said earlier. The fact that humans are able to discover these high-level abstract causal variables suggests that we will be able to find ways to do that in AI. Human brains are just complicated machines, and so we should be able to do it as well. It might take decades, it might take centuries, but we can. Another aspect of causal variables that is very important and comes up more clearly in reinforcement learning is the notion of agency. A few years ago, I wrote a paper with my collaborators, including my son Emmanuel and also my PhD student Valentin Thomas and others, about the notion of independently controllable aspects of the world. And in those days, I didn't know much about causality. I didn't know much about system 1 and system 2. I was about to discover these things. And the idea here is that not only we care about abstractions on the perceptual side to describe how the world is, but also on the action side, which is how we can change things in the world. And so one property that we're looking for these causal variables is that some of them correspond to actions that influence, like think of it like a bunch of atoms that somehow we can aggregate something like their position and independently control, say, this particular object, which is this bunch of atoms, from other aspects. So remember, this is connected to the idea that in the ideal representation, the actions are only going to touch one variable. And that means there's a way for an agent to just change one thing in the world. And a thing is precisely this collection of lower level things like atoms, which has the property that agents can do a single controlled action that can lead to just this thing changing. At least this is an ideal, and so this suggests a sort of one-to-one mapping between the way that we represent policies, which is really actions, extended potentially over many time steps, and how we represent the state of the world. So, the mutual information between these two things would be maximized if you had a bijection between these two spaces. In other words, for any object as in this high-level representation, any entity, any variable, there is a policy that will just, control that thing, and vice versa. For any policy, there is an object that it controls. And of course, you can make more complicated policies that can touch many things. But the idea is that this is the basic decomposition, and it's connected to the earlier independent mechanisms idea that I mentioned. It's connected to a notion in psychology called affordances, which is that the way we understand objects is through the different ways that we can control them. Okay. So an important aspect of this is really we're trying to answer a bunch of different questions now. We're trying to figure out how the low-level inputs and outputs of a learner are related to these high-level causal variables I keep talking about. So there's, to make things simple, we have this encoder and maybe decoder and policy that go from high level to low level and encoder from low level to high level. And also we need to figure out this sparse factor graph on the top level. So this is the job, right? And we don't have answers to how to do this, really in a large scale yet. So this is the kind of problem I'd like us to work on, and we have made a bit of progress towards, but really very small steps. So let's focus on this idea of localized causal interventions.
There's one.
Yes.
In chat. It's a longer one. So in physics, the concept of renormalization or real normalization group flow, where collective degrees of freedom, the equivalent of higher level abstractions in ML, can be found algorithmically and automatically. The concept of fluid comes automatically from the microscopic level mechanical laws that govern small water molecules, for instance. Do you think something like this could be useful for finding causal variables?
I'm pretty sure it can serve and has already served for some people. There are a lot of physicists in machine learning. So I'm pretty sure that these notions from group theory and physics have been inspiring people like Max Welling, for example. think about these sort of things. And a lot of work, even before machine learners started thinking about causality, the notion of invariance and equivariance and so on has drawn a lot of analogies and inspiration from the corresponding notions of groups in math and physics. I'm not the expert in these topics, but yeah, I think the connection is pretty strong, but I don't think it's sufficient. So this is the notion of local intervention. Like we're going to do something to one of those nodes, and that's going to create the change in distribution. And again, an example to help. If we have the right decomposition of knowledge that has this locality property, it's going to be much easier to adapt. So as an example, if I put on my dark glasses, all the pixels now have a very different distribution. Now, of course, you and I know that this looks like a big change, but it's really a small change. It's a small change because it's really one bit that changed in the right space of representations. So the name of the game here is how do we discover those representations, this space of variables where this kind of thing is going to be true, that changes in distribution can be pinned down to single variables or very few ideally. And there's an interesting way to think about this is that if you had the right space and the change was localized, then you would need few bits to account for that change, as I said earlier. And that means you would need few examples to recover from that change from a machine learning perspective. When there's a change in distribution, your predictor is going to get worse. Now I'm going to see new examples of the new distribution. How fast do I recover from that change? Is going to depend on me having a good representation of those variables. Oh, no, not again. This thing is starting by itself. Sorry, guys. Let me just shut him up. All right. So let me share again.
And in this time, there's been another question, which is what?
Please go ahead and tell it to me.
What does localized change mean?
Okay. So localized means only one or a few places in the graphical model have been modified. Is that clear? I mean, so like one variable is the most localized you can have. By opposition to everything changes when if my space of representation is pixel space and I put on my dark glasses, the marginal distribution of every pixel and their joint goes just haywire. This is not a good space to represent things. At least it's not going to help me deal with those very simple changes in the world. Okay. So we could measure how good is our representation by measuring how fast we recover from these changes in distribution. And then, so that's, if you can measure something and you know that when you got good values, you got a good model, then the next question is, why don't we optimize our model with respect to this? So what I'm saying is, let's train our causal model, including the encoder and the causal structure, causal graph, so that we minimize sample complexity due to, after a change due to an intervention. And that was the subject of this paper published this year, but really came out on arXiv almost 2 years ago.
We don't see your slides, but
yeah, it skipped slide, but I'll come back. Don't worry. So I'll come back to that paper, but we just studied a very simple scenario with two random variables A and B that are the causal variables, and potentially two observed variables X and Y. And we show that we can exploit this notion of speed of adaptation to guess the right causal direction and also to guess a good transformation relating A, B, and X, Y. So
We can't
yeah.
see your screen at all.
I don't understand what you're saying.
We can't see your screen. We're just seeing you.
Oh, okay.
Yeah, the share screen went away.
Fix that. I need to share again. That's what it means. Here. All right. So I was showing this slide. Sorry, that's the iClear paper this year that I mentioned. A meta transfer objective for learning to disentangle causal mechanisms, which really for me was a major starting point for this line of work. Really, there's the earlier paper on the consciousness prior that is behind that in 2017, but this really is focusing on the causality aspect. So this paper and others are trying to perform causal induction from interventional data. So we're going to assume that we can observe changes in distribution. We're also going to observe the data, before interventions. So that's observational data. But we know that's not sufficient. You can only distinguish causal models up to their Markov equivalence class, as I assume you've seen in this lecture series. Now, we wanted to be as realistic to the AI scenario as possible. And in the AI scenario, if you're a robot that's learning, like a baby robot, you may not know, at least at an abstract level, what was the intervention. Whereas if you're like a scientist and you design an experiment, well, of course you know what are the variables that you intervene on. So in classical causality work, typically assume that you know what the interventions are. Whereas in our case, we're only going to assume that there was an intervention. We don't know on which variable. And so then we have to do some sort of inference. We observe the change. We know potentially when it was, although in real life, this also has to be inferred, that there was a change. And then we have to figure out which variable was modified. And so many of the algorithms we talk about do that. So there's this one. I'm not going to have the time to go through a lot of the math detail of this, but I encourage you to look at the paper. I'll only kind of highlight one cool aspect of it, which has to do with, why is it that the causal model is generalizing better out of distribution and adapting faster? And it has to do with the fact that if you only modify one of the modules with the intervention, because the other modules are already kind of learned, the gradient on them will be zero. So there will be significant expected gradient only on the modules that changed, if you have the right decomposition. If you don't have the right decomposition, then you see on these curves that the adaptation is slower. So the x-axis here is number of examples on the log scale. Exponential scale, and y-axis is log likelihood on the new distribution, and we see that the causal model adapts faster. You might not benefit from that fast adaptation if you had just the reverse, the anti-causal model. And in general, what happens if you have the wrong causal graph is every part of the model becomes responsible in little part with respect to the change that happened. And I think that gives rise to things like catastrophic forgetting, poor transfer, and so on. I'm not going to go to more details of that to have time for talking about more things. So we also experimented with learning not just the causal direction between A and B, but also how A and B might be related to observed X and Y. We don't observe A and B. Somehow we have to figure out the relationship between A, B, and X, Y. X, Y is observed. So we're going to learn an encoder that maps XY to some UV, which hopefully are related in a simple way, like a permutation with AB. And the objective function of essentially good out of distribution generalization and out of distribution adaptation seems to work in this very, very simple setting. And it remains open work to extend these kinds of ideas to larger networks. We've extended it to large networks on the side of learning the causal graph, but not yet on learning the encoder. Just we haven't done it yet. So that's the work on larger graphs led by Rosemary Kay and a bunch of other authors, where we use similar ideas to either complete graphs that we have partial knowledge over, or to discover completely from ab initio the full structure of the graph. The kind of algorithms we use are illustrated in this figure, where we have, first of all, a belief over all graphs. Now that there's an exponential number of graphs. And so we represent that belief in a factorized way. So for each edge, for each directed edge, either it's present or not, and we have a probability over that event. So we keep track of those probabilities. So at any time we have a distribution over all the graphs, and we adapt those probabilities to maximize, how well you're doing on a modified graph. And we exploit properties of those changes, notably that what's happened in the modified graph doesn't tell you much about the mechanism that was changed, because it's not, it might be a different change next time, but it still tells you something about the other mechanisms that weren't changed. And that's essentially what we exploit. And from those ideas, we can come up with a gradient estimator that we can do gradient descent on. Also, the way that we parameterize this structural causal model is with neural nets. So we parameterize the joint with a bunch of conditionals, as you normally do in structural causal models. And each of these conditionals is represented by a neural net that can potentially take all the other variables as input. But depending on the graph structure, which we're now going to sample from our distribution over all graphs, this is what we see on the top here. We have a distribution over all the edges, probability being present. We can sample a graph, and then that creates a sort of mask at the input of the neural net, saying, well, you're only allowed to use these inputs for, if we believe in this graph. And then we're going to measure how well you're doing on the modified distribution. And that's going to give us a signal to either increase or decrease the probability of that particular edge that was used, that was present or not. This is kind of a summary. I'm not going to go through the experimental details. Sorry about that. I'm speaking too much. Yeah, let me skip this. Simple mapping between high-level semantic variables and language. I've kind of mentioned that already. The only thing I want to add is when you think about it this way, it should really change the way that we're trying to do natural language understanding. If we want to understand language, we also need to understand what words refer to. And the semantics of those words is not only defined in the relationship of the words, with other words or other related concepts, but also what these words refer to in the world, right? So in other words, if you want to do natural language understanding, it's not enough to understand here. It's not enough to just understand, build the right graph here. You also need to have the right encoder and decoder to anchor the meaning of those words in, things in the real world. So that's what I mean. This is called grounded language learning, where you couple text data with things like images or even better, an environment where there's also actions. Yeah, I already mentioned attention. I won't have much time to talk about it. It's really a tool to build neural net architectures that can lead to the kind of modularization of knowledge that I alluded to in the beginning of my presentation. What really happens is attention allows you to create dynamic connections between modules. It creates competition between modules, which one is going to send its output somewhere. And it creates a need for some sort of interaction, because the receiving module in this figure doesn't automatically know where the numbers that it's getting are coming from. And so the best way around this is somehow in the message that is being sent from the sending module to the receiving module, gated by attention, there is information about not just values, but also like names. Where is this coming from? What object is it we're talking about, and so on. And so another big piece of work that's inspired by this notion of independent causal mechanisms is a series of papers that started with this archive paper not exactly a year ago, but a bit more, called Recurrent Independent Mechanisms, where we explore recurrent neural net architectures where the modules are connected through these attention mechanisms to force them to compete to grab sort of the conscious attention and to communicate indirectly through these dynamically selected channels. So that is working quite well, and it's connected to theories of consciousness that I mentioned. We have this bottleneck of processing that's central to the global workspace theory of consciousness, and it's really attention mechanisms that select which part of the brain is allowed to speak loud and broadcast its content to the rest of the brain. So we've created a version of the recurrent independent mechanisms, the RIMS, that has explicitly this constraint, and it helps to deal better with out-of-distribution generalization. Let me skip this. Shared rules. I've skipped that. I'm going to skip that as well. Fast and slow weights. Stable things like causal structure should be like slow weights. And graded assignment over short causal chains. I actually put the slides on that, but I won't have time to talk about. I'm going to talk about this. So now this going back to causality. So here's a mental picture I have about what your brain may be able to do, which it's not clear how to do yet with algorithms and neural nets. Somehow we store in memory these past events. So these are like the little purple circles. So an event isn't the full state. It's what people in RL call the partial state. It's what you have in mind at a particular moment involves only a few variables. So an event involves a few variables, and it's like a small configuration, like a one-sentence thing, a thought, and it corresponds to maybe something happening in the world. The x-axis here is time. You're storing those events in memory. Those are selected by attention, and then you find connections between old events and new events, and that allows you to do credit assignment. You also find connections between old events, current events, and future events. I mean, in the sense that you're imagining what could happen. You can do counterfactuals in your head. You don't not only store those events, but you store these factors, these factor graph mechanisms that link events together. And of course, the same mechanism can be used over and over in different parts of this graph. if the appropriate typed instances show up. So being able to dynamically build this graph, and it's a huge graph. We don't need to instantiate completely, but we're going to be visiting parts of it as we're thinking in order to solve problems. And one aspect of being able to do inference over these kind of graphs is that searching through, say, possible futures is inherently intractable. And that's what you need to do when you reason and plan and look for latent explanations. But your brains seem to be able to do that very efficiently. And it looks like it's doing it by having system one generate good candidates for these edges and events and values of latent variables in that graph. So that's going on in the system one, and system two, conscious processing, is involved to evaluate those events. Like, you think about a potential path to go back home because there's construction on your way. And as you visualize the path in your mind, you realize, oh no, it's not going to work because we're Sunday and there's this other thing that blocks the path. So this is where the global communication of the global workspace theory is necessary to make sure that any module can express itself and say, no, this is not coherent. It's not consistent with the rules I know. And attention mechanisms are used to give a voice to those modules that need to speak up and say, no, this is not good, or here's a good alternative candidate. There are lots of connections between what I said and classical AI, classical symbolic AI, but also a lot of differences. So ideally, we want to keep the advantages of modern deep learning, like large-scale learning. We want to ground these symbols in system one. We want to take advantage of distributed representations to get better generalization. We want to use system one to propose candidates to make the search efficient, like in AlphaGo. We want to be able to handle uncertainty. So these things were lacking in classical AI. But we want to add these things that rule-based logical systems have, but not, they lack the learning as well. So systematic generalization, factorizing knowledge in small exchangeable pieces, and being able to manipulate variables, instances, indirection, and so on. That's it. We have a responsibility. Be good boys and girls. And now I have only 8 minutes for you guys for questions. I'm sorry I spoke too much. I see one here.
Okay.
About Roger Penrose. Yeah, I do disagree with Roger Penrose. I mean, he's a very smart guy, but he's not a machine learning researcher, and he's not a neuroscientist. So I think he's speaking a little bit out of his field, and he's trying to squeeze something he loves and likes, which is special properties of matters coming out of quantum physics, and hypothesizing that these are important for consciousness. I think it's a little bit ludicrous. Maybe it's true, but there's no any strong evidence for this. And so, as an Occam's razor fan, I would say let's try to explain conscious processing using like normal physics. I mean, there is quantum physics going on everywhere because you have molecules and molecules strongly influenced by quantum physics. But I mean, beyond the locality of what's going on at the molecular scale. And maybe we won't be able to explain it, but I think we're now converging to a scientific picture of consciousness, which doesn't require any of these fancy stuff, non-local computation and stuff.
Would you mind reading? If before you answer the next question, would you mind reading it?
Oh, sure. Yeah, I mean, so Roger Penrose argued that consciousness was not computable with a Turing machine. That's what I was trying to address. The next one is, to what extent should we think of an agent's actions as interventions, and should an agent think of its own actions as such? Yeah, I totally think that actions are interventions. Now, if you remember one thing from my talk, or at least a few things from my talk, one of them is we should distinguish these high-level abstract actions that correspond to an intervention in the sense that they really are about modifying one abstract causal variables. Like, if I say, the intervention that's going to push my cup off of the table. Somehow it's very tempting right now. But there's also the low-level actions. Like, actually, this isn't what is going on, right? What is going on is my brain is sending these millions of signals to my nerves and muscles and so on. So there's like a high-dimensional, low-level space which is implementing this thing, and so the abstract part where we can interpret the actions as interventions only works if you're doing it in the right space. So if the action space is my muscles, then it's not interventions in the usual sense of causality. And that's why the representation part of it is so important. The next question. What are possible learning rules for the combined system 1 and 2? Is gradient descent sufficient? Yeah, gradient descent is sufficient, I think. I mean, with whatever variant of gradient descent. I mean, already today we use some sort of tweaked gradient descent. What is less obvious, I mean, going down the gradient is like a no-brainer. You want to do that. What is less obvious is what objective function we should optimize. And of course, people in machine learning have been coming up with things like this. It gets less obvious in the unsupervised case. Like, if you think about an agent that's just trying to explore their environment, like a baby playing around and making sense of their environment, what is it they're optimizing? This is a good question, and we have some ideas, but it's really an open question. We don't know. We don't even know how to do it well for machines, let alone explaining how children do it. Next question, how can we deal with confounders when doing causal discovery in the causal semantic representational space? It's a good question. So I talked about a couple of papers, in particular the papers with Rosemary Kay as a first author, which you can find in archive. Where we look at these larger graphs where there are confounders. So with 2 variables, there are no confounders, obviously. But as soon as you have 3, but anything larger as well, you have confounders. And somehow it looks like this idea of taking advantage of the locality of the change to direct how to learn and to provide a learning signal seems to work in figuring out the causal graph, even though there are confounders. I can't give you like a precise causal chain of how this is happening, but it seems to work. Next question. What would be your advice to the people who are working in research areas like computer vision and NLP to get started with research in causal learning? Well, you already did the right thing to come to those lectures that Brady is organizing. So it's as usual. If you want to learn about a new area, read, engage with people who are working in it, eventually get your hands dirty and so on. There's no secret, hard work. Next question, can you explain the connection between attention and causal inference? Right, so causal inference is a general goal. We're trying to achieve something, answer questions about a causal graph. And attention is a particular procedure or mechanism that the brain is using, and we're starting to put in deep nets with great success, but not yet much for causality. So one is sort of what we're trying to achieve in mathematical terms, and you can have many algorithms to do that. And then it happens that brains seem to use as in its algorithms makes heavy use of attention. And I think there are good reasons for that I try to explain, because it may help to enforce the sparsity of the learned causal graph. Next question. You seem to focus on causal discovery more. Do you think there are more identifiable causal relationships in the structure of observational data than we can prove now? Not sure I understand the question. Do you understand, Brady? I mean, not everything is identifiable because there are non-observed variables. So as soon as you do interventions, in principle, you should be able to recover the whole causal graph if you allow yourself enough interventions on everything. If you have latent variables, in other words, things that are happening in the world that you don't directly observe, or you have uncertainty over, then it's not clear that you will be able to identify the right causal graph. And yeah, that's all I can say. Next question at the end, you mentioned that we have a responsibility. Sorry, I went too fast on that. That will be another lecture. How do you think that causal inference can help us addressing our responsibility regarding the ethical dilemmas that current AI create? Very indirectly, by thinking about the effects of your actions as a citizen, as a researcher, as an employee of a company, as a person who participates in debates and so on. But as such, I think if more people, more citizens understood the basics of causality, we might have less demagogy being so strong as we're seeing these years. Next question. On slide 21 and 22, you talked about pixel space and how it is a bad representation to deal with changes, such as putting dark glasses on. How should we go about finding good representations? Well, I suggested one way. There are a bunch of papers already that are proposing ways to discover the causal graph. And the particular work I mentioned exploits the locality of change assumption to come up with objective functions that you can just do gradient descent on once you can write it down and do the math. And at least on for the learning of the encoder, we didn't do a lot of experiments, just the two causal variables experiments that I mentioned. But I think we should really push forward in that direction. Next, we can learn causal models if the confounders are observed. Yeah, the question really is about how to learn a causal model if the confounder is unobserved. Right. I don't know, but one good step towards this is to create a latent variables in your model. Right? So in any case, already in a way, when I create that structure where you have an encoder and the latent variables, I mean the causal variables, they're not observed really, because the mapping from the data to the causal variables is not known. Now, in addition to the mapping not being known, there may be uncertainty about the values of these variables. We haven't really played much in that direction, but I think it's super important. It's also tricky because the inference mechanisms, the kind of assumptions we might need to do to deal with that, really, I don't know. I don't know how to do that. But I think there's a lot of experience in the last few decades in inference mechanisms for graphical models that we can draw from. I mean, the easiest way is to do some sort of sampling methods, but it tends to be inefficient. But maybe the saving grace, and maybe this is one of the reasons why the brain uses this low-dimensional representation stuff, maybe the saving grace is that the sparsity of the graph, right? Because locally the inference is going to be easy because it involves very few variables. Maybe there would be algorithms that work well in this case. We know that in graphical models inference could be very, very difficult for some graphs and very easy for other graphs. I mean, trees is being, an extreme case. So what about very sparse graphs? I don't think we have answers for this, but I suspect that they may have properties that allow us to do efficient inference, efficient probabilistic inference. Right? So in other words, deal with latent variables. Last question I see. Does it mean from causal perspectives that model-free RL is not so useful and we should force agents learn causal graphs instead of just transition distribution? So first of all, transition distributions are not in model-free RL, they're in model-based RL. And I think we need both model-based and model-free RL. And when you do model-based RL, so learn the transition distribution, yeah, I think you should learn a causal graph, and not just P of next state given previous state, but that, the graph that I had at the end, the structure that can generate that graph, those mechanisms and the inference mechanisms for it, that's what we need to learn, rather than the simple-minded, ST to ST plus one homogeneous big conditional. If we have unlimited raw high-dimensional data, can we potentially extract all confounders of raw? So if you observe all the causal variables, I think this is a well-known result. Yeah. As I said, I don't think we can say much if you don't. Okay. Thanks, everyone.
Yeah, thank you very much, Yoshua. There will be lots more people seeing your talk online, and as you could say, lots of people are thanking you in the chat.
All right. Thanks, everyone. Thanks for your questions. Bye-bye.